So market size is currently about 10 million proofs per day, which makes around $5.5 billion per year. But it's expected to grow to up to 90 billion proofs, which makes something like $10 billion market by 2030. This actually depends on the cost of specific proof, right? And we are the guys who are trying to make this cost as low as possible. What are actually perspectives and what we can do in this sense to further actually enable something that we call commoditization ZK and indirectly wide adoption of the technology? So basically, as John correctly pointed out, it's necessary to adopt end-to-end and fully optimized approach that actually matches dedicated infrastructures so that the most cost-performance solutions are delivered in this sense. There are many various approaches, starting from GPUs. Actually, GPUs were the first ones to be introduced in this kind of field. And of course, on the other side of scale, we have ASICs and all possible hybrid approaches in between, including FPGAs that is currently focus of our strategies that we are applying in this field, and I will explain later why we are actually focused on FPGAs. So anyway, such custom-built solutions differ in both cost and latency. Some of them are less costly, some are on a higher cost, on a higher latency, and vice versa. This is actually the basic foundations of something that we will have in future as proving markets, not so much a far future, I hope very near future. And this basically is driven by several different kinds of proving demand sources. First of all, these are application-specific projects, mostly DeFi projects. Then main flagship projects like ZK Sync, SNARKtor, Polygon, and RISC-0, and so on. And basically, there are some use cases that really require this. It's, as I mentioned, mostly DeFi, the regular fintech, as well as privacy-preserving machine learning and fintech is, for instance, compliance, and we are involved in a few projects of this sort, basically in regular computing. On the other side, yeah, there is a very growing interest also from main technology providers like AMD that are coming to us and offering different kind of collaboration, and this is something that is very promising and gives us a lot of hopes that we will basically manage to cope up with this kind of problems and challenges that we face in this kind of field. So, when we speak about ZKVMs, I actually have stolen this from Lita website. Credits to them for this. What we have most of you actually, I hope, are aware of the fact that we have a general purpose program in Rust and whatever. We have compiler that builds machine code or bytecode, and then there is a VM that is producing trace. This trace is the main input for provers, in which in the first step, like arithmetization, the trace is translated in polynomials, constrained polynomials, and this is called, by the way, front end, and in back end of the prover, in which we are mostly focused, we will see more details later, this kind of polynomial, there is something that is called low degree extension, and basically starting from that and many different operations, including Fiat-Shamir at the end, we are actually, we provide final output that is a proof, and as a final step on the other side, we have verifier that takes this as an input and checks basically correctness. So this was very, very brief and general overview of how ZK proving works. But basically, as I mentioned, it's divided in two parts, mostly front-end and back-end, which is practically back-end is mostly polynomial commitments. And in this sense, we basically have two mathematical algorithms on which these kind of commitments are based. First of all, it's a discrete algorithmic problem that is performed basically on elliptic curve pairings, and these are practically relying on algorithms like MSM, which is multiscalar multiplication, and in practical terms, practical implementation of that is KZG, mostly, especially in the Ethereum world. And most STARKs are actually based on that. On the other side, we have STARKs that are based on error connection codes and rely on hashes. And this is something that Telos is using, and this is something, luckily, that we are providing the most performant solutions in this field. All these kind of algorithms have different computational, communicational, and memory requirements, and they are pretty high, all three of them. And general purpose computing is absolutely not suitable for computing this kind of stuff, for actually facing this kind of requirements, computational requirements that are coming from whatever kind of ZK Brewing algorithms. Then another problem is when it comes to hardware acceleration, there is always a moving target. In the sense that even one bottleneck gets completely eliminated, it's just a part of proof. So if you have, for instance, an entity that makes, let's say, 50% of a proof, you accelerate it 100%, which is theoretically not possible, down to 1%, you still have just 50% saving in terms of entire proof. And what are the critical ZK primitives actually that are causing bottlenecks in software execution? First of all, it's hashing, and that is incredibly computation expensive in common CPUs because it involves extreme number of wide integer multiplications and additions. The same goes with the low degree extension, which is performed practically with entity, number theoretic transform, that again involves huge number of wide integer multiplication and additions, and a part of that is very, very memory requiring. In particular, requires fast memory due to incredible number of transformations, actually namely transpositions in this case. And finally, then it is MSM. That is operation that requires huge time in ZK computation, but as I mentioned before, it's foundation of SNARK, so I won't spend much time on that because we are almost completely SNARK based actually in our both in both use cases that we actually performed so far and that I will present here, Polygon and SNARKtor. So, as I mentioned, hardware acceleration was based on a GPU. I was started with GPUs, and currently the focus on FPGAs. And ASICs are still not in the play just for the reason that ZK algorithms are not standardized. We don't have actually still the common consensus on what kind of algorithms are going to be used. So that given the fact that the field is very fastly moving on a fast pace and very dynamic, it's still too early to speak about ASICs, so that FPGAs are becoming actually the leading flagship solution in this sense. The very suitable components of ZK stars, actually hashing an entity, are very much parallelizable and very much possible. It can be parallelized and pipeline, which is foundation cornerstone for suitable FPGA acceleration. Out there, we had the market, we had the broad range of powerful FPGAs, and we are actually trying to find the optimal solution, the optimal choice of these kind of cards to couple them with CPU host in a proper way so that we make the fastest solutions as possible. What we managed to do actually, we managed to perform 10 times faster computation of caching, at least 10 times, we'll see later depending on some factors, than the fastest ones in whatever CPU or GPU configuration. We significantly managed to cut both latency and cost, and that's something that you can achieve basically given the currently available technologies only with FPGAs. On top of that, FPGAs are offering significant energy cost, energy consumption savings as well, making all these computations greening, which is also important to the good of our society. What's fundamentally new that Ponos Technology as a company brought in this field is actually something that we can name a comprehensive approach or end-to-end co-design, hardware software co-design approach to acceleration. So far we had partial ad hoc acceleration on some modules, which basically does not give so good results. So on the other side, what we did, through modular design, we basically accelerated each single component, but moreover, we actually optimally fine-tuned the memory footprint and entire memory formats, memory streaming, so that entire control and data flow in the proving process is optimized with respect to hardware accelerated components, which yields the best, the most performant solutions. We are also, on the other side, we are adopting, this is, let's say, horizontal scaling, but there is also vertical scaling in the sense that we start for optimizing basic cryptographic primitives. For those who are familiar, for instance, MDS and S boxes in Poseidon hash, we fine-tune those parameters to be the most hardware-friendly. Up from this very low-level primitives, we go all the way along through the entire implementation design flow up to final deployment scenarios, so that it's absolutely both horizontally and vertically optimized system. And finally, we are also optimally matching execution environments in sense of host system, meaning CPU, accompanied with the proper memory. On the other side, FPGA card. I don't know how much time I have left.
Not much.
Not much. Okay, these are some results, and this is the most important thing. And at the end of the day, it's all related to business. So we are speaking here about Polygon ZK EVM, which is the baseline, something that they are actually using now for calculation of proofs. You may see, there is laser? No. Okay. In this line, you basically can see what Polygon is actually paying now per year. Let's consider only this number. Let's consider actually two numbers. This is the latency. This is how much time they need to calculate the proof. And this is actually what we got. And this is the amount of money they pay per year for proving. And this is the amount of money they should pay considering our solution. Finally, this is actually the newly provided, newly released AMD card. This solution is actually calculated, not performed, but everything in this table is absolutely implemented. We have demos, and it's possible to try for those who are interested. So savings are obvious. You basically save more than 6 times using this kind of solutions, and you basically cut latency for 40%. I'm not going into details how much each primitive has been accelerated. It's more than 10-20 times, but as mentioned before, those primitives actually are taking 40 or 30% of entire prover. So these are savings at the level of entire prover, not considering all these optimizations inside included. Finally, what we are doing for Telos. This is SNARKtor, for those who are at least familiar with it. This is aggregation layer based on recursive proving. And basically what SNARKtor is doing, it's trading proving cost for lower verification cost. Meaning that if we manage to decrease radically this proving cost here, we are gaining twice. We are decreasing verification, and on the other side, we are also decreasing verification cost, and we are decreasing also proving cost. Basically, it's a kind of win-win solution that makes SNARKtor and Telos as a project the most performant project in terms of 3 basic metrics that I mentioned at the beginning: TPS, cost, and latency. This is how it's technologically enabled. So these are some numbers. Basically, we managed to cut the cost, proof time, for disaggregation for more than 60%, accelerating specific components more than 20 times, for instance, for Poseidon, and 10 times for LE. Just the future, so I have 30 seconds, I hope. Thanks. So basically, the future is that we need real use case that will actually make this ZK proving exploding, that will create this kind of that will make proving markets a reality. And in that case, all the provers will compete by providing lower cost or lower latency solutions. And that's something which is the next, I would say, stage for Ponos Technology. yeah, for wide adoption, of course, we need user-friendly front ends coupled with efficient backends. That's a kind of winning game in this case. Analogically to AI, I would say that progress in algorithms coupled with advances in underlying hardware enabling that would create break-even point. And yeah, we are building dedicated, fully optimized ZKP infrastructure and for proving markets that we sincerely hope will come soon. And yeah, finally, I do believe and I hope that all the different kind of research and development efforts done in many different projects will somehow coordinated or orchestrated, or at least we are open to collaborate with all of them, all of you guys, so that we all together bring, make ZK widely adopted technology, enabling nice future for all of us.